Welcome back to episode 2. Maya and I are on this journey with you to try to figure out how the climate changes we are personally witnessing today compare to the changes the Earth has experienced in the past. Some sources we see online claim the rapid changes in the planet are just normal, but something really doesn't seem quite right to us. We thought it would be better to analyze the data ourselves and then decide.
In episode 1, we met with Carly Peltier, a climate scientist who claims that evidence of climate change in the past can be found in the mountains of Patagonia. Sounds like a great place to start. Let's join Carly and do some science together.
Welcome back to episode 2 of this virtual field lab series. I'm Carly Peltier. I'm a climate scientist at Dartmouth College. And what we're going to look at today in episode 2 is how the climate changes of the past compares with the climate change the Earth is experiencing today. We know that climate change is nothing new. The world that allowed dinosaurs to roam the Earth and monster trees like sequoias to dominate the forests must have had really different climates and been a really different world than the world we live in today. And another way that we know that the climate has been different in the past is by studying the land surface, by looking for evidence left behind by glaciers. Our planet is a really special place. The Earth is unique in that the surface temperature is close to the freezing point of water, which means that small changes in the global temperature can cause massive ice sheets to cover the poles and for glaciers to grow in the mountains. So small changes in temperature can cause glaciers and ice sheets to grow and advance or melt and retreat. One place to look for evidence of climate change in the past is in Patagonia. Patagonia is a region of southernmost South America. It's the southernmost bit of the American continent, and it's super beautiful. It's a really cool place with huge mountains, and so when it's gotten colder, an ice sheet has covered those mountains and almost all of the land. Glaciers and ice sheets are great at leaving behind evidence of what the climate was like in the past. Glaciers are super cool. They're made of ice, but ice that's so thick that it flows under its own weight like a slow-moving river. And as a glacier flows, it picks up rocks along the way, rocks and sediment and even things as big as boulders. And those rocks flow with the glacier until they reach the edge of the glacier, where they get dumped in big ridges called moraines. So the really neat thing is that in a lot of places, like in Patagonia and the northern United States, where I am today, you can find these ridges of jumbled up bits of rock that were deposited by glaciers, but in places where there are no glaciers today. So that tells us that sometime in the past, glaciers were much bigger than they are today, because these ridges or moraines mark the most expansive extent of the glacier. And then when it warmed up and temperatures rose, the glaciers melted and retreated, leaving behind these moraines. In this virtual field lab, we are going to look at evidence in the rocks deposited by these glaciers to try to understand what the climate was like in the past, what the climate change of the past has looked like. And then we're going to compare that with the climate change of today to understand if this kind of climate change is normal for the Earth. When we look at the land surface in Patagonia, we don't just see one moraine ridge. We see whole sets, whole sequences of these moraines. And by just looking at them, we can't tell whether or not these were all formed during the same cold period and they just represent small changes in the extent of the glacier, or if each one of these ridges represent separate ice ages. To decide which story is correct, we need to be able to figure out how old the moraines are. We need to be able to tell time. And lucky for us, we figured out a way to determine how long a rock has been sitting in a moraine. The technique we're going to use is called surface exposure dating. Surface exposure dating looks at how the chemistry of a rock surface changes when it's bombarded by cosmic radiation. Here to tell you more about surface exposure dating are some of my climate science friends out in Oregon.
All right, hi everyone. I'm Ben Riddell Young. I'm a graduate student at Oregon State University, and these are my climate science friends.
Hi there, I'm Katie from Oregon State University. I'm Camille from Georgetown University.
And I'm Sebastian from Oregon State University. So we're sitting here today on the shoulder of Mount Hood, and behind us we have the Elliott Glacier. And right here we're sitting on something called the lateral moraine, which is the side of the glacier where a bunch of rocks were dumped. So we know that in the past the glacier was about this high, dumping rocks on the side of the glacier, but today it's much farther back. So we've been sitting on this rock here for about 5 minutes, but what we're here to find out today is how long this rock has been sitting here. And to do that, we use this technique called surface exposure dating.
Let's take a closer look at how the chemistry of surface exposure dating actually works. Many boulders dropped by glaciers contain the mineral quartz. The mineral quartz contains atoms of oxygen.
So this rock was carried down by the glacier, plopped on the side of the glacier, and now that it's sitting here, it's exposed to the sunlight that hits it. And in addition to the sunlight, we also have this stuff called cosmogenic radiation that comes down and bombards the rock while it's sitting there.
One type of cosmic radiation that hits the rocks are super fast-moving neutrons.
When a fast-moving neutron hits the nucleus of an oxygen atom, 3 protons and 4 neutrons get blasted out. What's left is an atom with 4 protons and 6 neutrons. Oxygen becomes beryllium-10.
In Patagonia, beryllium-10 production happens at a rate between 4 and 9 atoms of beryllium per gram of quartz per year. The beryllium-10 production rate depends on both the altitude and the orientation of the boulder.
The longer that this rock sits, exposed to cosmic radiation, the more beryllium-10 builds up.
This means if we can figure out how much beryllium-10 is in a rock, we can figure out how long ago the glacier melted and dropped it there. That's a pretty cool technique.
Now, let's go back to Carly in the lab, and you can help her calculate what climate was like in the past based on rock samples that she collected in Patagonia.
First, we need to pick some specific sites to sample. In the region of Patagonia that we are studying today, what we find is a really long sequence of moraine. So it's just moraine after moraine in this nested sequence, and we don't know if those moraines were all deposited in the same overall climate event, or if each moraine represents a separate ice age, for example. So let's see which story the evidence supports. Let's collect 3 rock samples from the first moraine. And so we're going to find a nice big boulder that looks like it has been in the same place since the glacier left that spot. And to sample the rock, we're going to climb on top, and we are going to drill a little hole, and we put a little tiny explosive in the hole, and then we detonate it. So we blow off a tiny little bomb on the surface of the rock to blow off a little chunk of rock that we take home back to the lab. So now that we're back in the lab at Dartmouth, and we've got our rock samples from Patagonia, and what we need to do next is we need to separate out just the mineral quartz from this rock, because that's where the beryllium-10 is accumulating as it was exposed to cosmic radiation. So now we've got all of our samples on the shaker table. So each one of those bottles has a different rock sample from a different boulder in it. We added hydrofluoric acid, which is going to dissolve all of the minerals that we don't care about, but it's going to leave behind the quartz. Once we've gotten rid of the other minerals, we're left with this nice pure quartz. And the next step is going to be to dissolve this quartz in a really nasty acid to separate out just the beryllium. So now that we've dissolved our quartz in hydrofluoric acid, so we turned it from a solid into a liquid, we're going to put each sample into its own column over here, which is going to help filter out all of the elements that we want to get rid of besides the beryllium that we're going to measure on the mass spectrometer. And so that's what my lab mate Victoria over here is working on. So let's check it out. Now we're drying our samples down on a hot plate. We're going to dry these down so that we're left with just beryllium hydroxide. And then the next step is we're going to put them into tiny little containers, and we're going to put them in a furnace so that we're left with just beryllium oxide, which is what we will measure on the mass spectrometer. At this point, our sample is about the size of a fleck of dust, and we're going to put each one of those flecks of dust from each different rock into its own little vial, and we're going to send it to the mass spectrometer. A mass spectrometer has the ability to separate out atoms of different elements based on their mass and their charge. So beryllium 10 will get separated in the mass spectrometer and then measured to get the exact amount of beryllium 10 that was in our sample. So let's take a look at the data from the first set of rocks that we brought back from Patagonia and measured on the mass spec. We have beryllium 10 concentrations from 3 different rocks from each moraine. The first set of data comes from this moraine in pink here on my map. As you can see, there are moraines all over this area, but today, together, we're just going to date this pink moraine and this green moraine. We're going to make a table in our notebooks with 4 rows and 4 columns. The 4 columns in our data table will be the boulder name, the beryllium 10 concentration in atoms per gram of quartz, and then the third column is going to be the production rate in atoms per gram of quartz per year, and the last column will be the total years of exposure. We measured 3 boulders from this moraine, this pink moraine, moraine number 1, and we're going to call them boulders A, B, and C. And by the way, this is our actual real data that the mass spec actually measured, which is pretty cool. Sample A from moraine number 1 gave us a beryllium 10 concentration in atoms per gram of quartz of 204,000. And for boulder B, we got 194,000. And for the third boulder, boulder C, we got 187,000 atoms of beryllium 10 per gram of quartz. We know that on average, about 8 to 10 atoms of beryllium 10 per year are produced in each gram of quartz at this spot in Patagonia. The production rate of beryllium 10 for each sample is a little bit different because I've corrected it for things like the elevation of the boulder that the sample came from, because samples at higher elevation have less atmosphere above them acting like a blanket to block the cosmic radiation. And I've also corrected the production rates for the sample positions on the Earth and what fraction of the sky around our sample is covered by mountains, which also blocks cosmic radiation. So the production rate I calculated for sample A is 8.64 atoms of beryllium 10 per gram of quartz per year. So now we can use this production rate to calculate how many years it would take for this much beryllium 10 to accumulate in our rock surface, which will tell us how long ago that rock began being exposed to cosmic radiation after getting dropped from the melting glacier. What we're going to do now to calculate the years of exposure for boulder A is we're going to divide the beryllium 10 concentration by our production rate, and the answer I get here is 23,611. And so let's check out the units here. So our atoms of beryllium 10 per gram of quartz on both of those numbers cancel out, and so we are left with years. And we're going to go ahead and round this number to the nearest 100 years. So I get 23,600 years. Let's go ahead and write that number down in our data tables. Next, we're going to do the same thing for boulders B and C. For boulder B, the production rate for that sample was 8.09 atoms of beryllium 10 per gram of quartz per year. So we're going to divide 194,000 by 8.09. So that rounds to 24,000 years. Let's go ahead and do that for our third sample, sample C. The production rate for that sample was 8.11 atoms of beryllium 10 per gram of quartz per year. We're going to divide the beryllium 10 concentration by the production rate to get the number of years of exposure. When I do that for this sample, I get 23,058 years of exposure, which rounds to 23,100 years. We did this 3 times because, as you can see, each boulder gave us a slightly different value. And what we want is we want an age that is representative of the whole marine age. So we want to get multiple values so that we know that our answer is correct. So this data tells us that sometime before about 23,600 years ago, the climate had cooled down a bunch to allow this glacier to flow all the way down from the mountains out into this valley. And then at about 23,600 years ago, the glacier started retreating and pulling back from this moraine where it left these boulders exposed to cosmic radiation.
Thanks, Carly. I think I get how the whole process of surface exposure dating is done. Let's see if we can analyze a second set of data from a second moraine. This moraine, colored green on this map, may have been formed during the same glacial period when the same glacier expanded and melted slightly, or it may have been left from two glaciers that formed during completely different ice ages. Carly blew off 3 rock samples from the second moraine and took each sample through the entire process in her Dartmouth lab. Here are the beryllium concentrations and production rates that she calculated. Let's copy this data into your notebooks and then pause the video and see if you can calculate the age of each sample, as well as the average age of the rocks sampled in this moraine. Pause the video while you calculate. Hit play when you are ready and we will see how your calculations compare.
Welcome back! Here are the ages that Jack and I calculated for each boulder, as well as the average for the moraine. Hopefully our numbers are close to yours. Let's turn this back over to Carly to see what she thinks of our data.
Wow, this moraine has been here for a very long time. This exposure age tells us that the glacier was much bigger than it is today, around 136,000 years ago, when the moraine finished forming and the glacier started retreating from this margin. Samples from moraine 2 have a lot more beryllium-10, and their ages came out a lot older. So we set out to answer 2 questions in this video series. The first was, what has climate change looked like in the past? And the second was, how does the climate change of the past compare with the climate changes that are happening today? So now in our data table, we have evidence for what the climate was like in the past. So on a page in your notebook, let's make a graph to tell the story of the climate of the past. So we'll put an X and a Y axis. The X-axis will be our time axis, and we'll label that with the years before the present. We'll start at 150,000 years before the present, and we'll mark every 25,000 years, so that we can fit all of our data on the graph. So we've learned a few things from our moraines in Patagonia. We know now that the average age for moraine number 1 plots right here, and so this tells us that the peak of the last ice age at this spot for these glaciers was 23,600 years ago. And it also marks the moment that the glaciers started retreating. So we know that the last ice age started ending at this moment. The average age for moraine number 2 plots all the way over here at 136,000 years ago. So this indicates that there have been 2 major ice ages, and that these 2 moraines represent separate ice ages instead of smaller scale climate changes within the same climate event. So this means that there was about 112,000 years between the peaks of the last 2 ice ages. Okay, so let's talk about the climate of today. We are super lucky to live during an interglacial period when the climate is relatively warm. We don't have ice sheets covering Patagonia and the northern United States, including New York City. This is what our early ancestors, early Homo sapiens, had to live through. But all of human civilization, all of the history that we learn about in history class, this has happened during this nice warm interglacial period. So we'll go ahead and label the period after the last ice age, the end of the last ice age, as the interglacial period. Between our 2 ice ages that we dated with the moraines was another interglacial period like today. Now we've captured evidence for 2 ice ages by directly dating them, and now we know exactly when they happened, which I think is super cool. So let's see what the CO2 record was like over this period so that we can compare it with what we now know the glaciers were doing in Patagonia.
Hi everyone. Carly asked if our lab here at Oregon State University can provide some data on carbon dioxide levels in the atmosphere going back 150,000 years. No problem. In fact, right behind me is a crusher where we actually crush bits of ice that we've collected from Antarctica. When we crush that ice, the air that is trapped inside gets released. We then measure that air using a gas chromatograph in order to determine the amount of carbon dioxide that is in that air. We'll then share that data back with you guys so you can add it to your notebooks. Okay, back to you, Carly.
So let's go ahead and add these data to our graph. So go ahead and label your y-axis going from 0 to 450. And the units here for CO2 concentrations are ppm, parts per million. So this is how many CO2 molecules there are per million molecules of all other gases in each of these little air bubble samples. Take the data that they measured at Oregon State and add it to your plot so that we can see how the timing of changes in CO2 concentrations in the atmosphere compare with what we know about the glaciers and the changes in climate that we reconstructed from Patagonia, from these moraines. And when you're finished, go ahead and hit play, and we'll see how our graphs compare. Hey, welcome back. So when I plot these data on my graph looks like this. So this is the last 150,000 years of CO2 concentrations in the atmosphere, combined with the story that these glaciers in Patagonia have told us about the climate history and about the ice ages of the past. And so now I would say that we have a pretty good picture of what climate change was like in the past. So let's go ahead and finish up our analysis of our data by looking at the graph. So let's start by writing down 2 things that you notice about the data and 1 thing that you wonder. So you can go ahead and pause the video while you write.
When I look at this data, it suggests to me that in the past, there have been really big climate changes where glaciers and huge ice sheets advanced and retreated, and these climate changes have been a pretty normal thing that usually occurs over about a time scale of 100,000 years. This makes me wonder about a few things. First, I wonder why climate changed every 100,000 years. I want to know what caused those changes so that we can understand how our climate system works. The second thing that this makes me really curious about is how the climate changes of the past compare with the climate changes that we're seeing today. How unusual is the climate change that we're seeing today? So come back in episode number 3 and we'll try to answer both of these questions.
Well, that was awesome. It felt great to analyze the actual data ourselves instead of just believing what different sources claim online. So now we know that climate change on the planet is nothing new.
So come back and join us in episode 3, where we will be looking at the data from ice cores to figure out for ourselves if the changes we are seeing on our planet today are anything like the changes we saw using Carly's data from Patagonia.
Okay.
You better been recording. Welcome back. We're... What?
That's a nice touch.
Okay, I just wasn't expecting. Okay. Sorry. I can't stop. Don't. Okay.
I know how long it needs to be. He told me how long it needs to be.
He told you?
Yeah.